Ladies and gentlemen, hello and welcome to One Take Studios, where I am having a rough day, so please bear with me and we're going to make this the best that we can. Alright, today's topic is curve fitting with quadratic models. Curve fitting, the idea of taking a mathematical model and fitting it to some data, and there's a whole bunch of different models that we can use, but today's focus is on quadratic. To make that happen, there's a couple of things I want to show you. The first one is something called finite differences. And this can be used for more than quadratics, but this is at least going to be an opening point for us on this particular topic. If I'm using finite differences to help determine an appropriate model, I want to have a set of data where the x values are all, can you figure it out? 1, 3, 5, 7, 9, where the x values are all equally spaced. Ladies and gentlemen, your x values must be equally spaced, not necessarily by 2's, but this whole thing is going to be a waste of time if they're not equally spaced. So that's the first thing you want to check if you're considering using finite differences, is that all of your x's are equally spaced. Now, differences implies we're going to use some subtraction here, which does make sense. I'm going to go ahead and subtract my y values, because I know the x's are good. I'm going to ignore those for now. I'm going to do 1 minus negative 1. I'm taking my y values and subtracting them right to left. Why am I subtracting them right to left? I'm not really sure. Every textbook that I've seen does right to left. I've done it left to right. It still works. So I'm not exactly sure what they're going for there. But that is a grand total of 2. Alright, and then that was so much fun. Let's do it again with these guys. 7 minus 1, that is 6. And these guys right here, we're talking 17 minus 7, that is 10. And then one last one here, 31 minus 17, which is 14. Okay. These are what we call the first differences. First differences, and I'm just going to abbreviate that. So, first differences. The idea that I did one round of subtraction with all of my y values. What does this tell me at this point in time? Not a whole heck of a lot, because what I'm really looking for is I'm looking to see a constant data set. 2, 6, 10, 14, those are not the same numbers, and so we are not quite where we would like to be. If these were the same numbers, let's say for the fun of it they came up as 6, 6, 6, 6, well, that would mean the first differences, first degree equation. Ooh, your first line of subtraction can tell you whether or not you have a good linear model. Linears are first degree. This is the first difference. So right now, if I look at this and I see all this variation going on, I know that this data is not linear. Okay, so while this doesn't tell us much, it does start us on the right track. We know it's not linear. One thing eliminated. Let's keep going. Subtracting again, we've got 6 minus 2, which is 4. And then we've got 10 minus 6, which, is 4. And we've got, hey guys, 14 minus 10, which is 4. That was our second line of subtraction. I'll give you 2 guesses. Anyone? Those are the second differences. Second differences are all 4s. That's that consistency we're looking for. And, okay, so if first differences, first degree, that determines linear. Second differences, second degree, that's quadratic. Quadratics are x squared. And so we can look at this and say, hey, this is a really great quadratic model. In fact, because all of these numbers are identical, this data set makes a perfect parabola. Great. Now maybe I go about trying to find the equation. That's the downside of finite differences. It doesn't find the equation for you. It's just like, here's some information. I do think it's fascinating because especially with future things, maybe you can even guess where this might be going. First differences are linear. Second differences can tell you if it's quadratic or not. Because if this wasn't quadratic, if these numbers weren't the same, maybe I would keep going. And maybe third differences might tell me cubic. Ooh, that's an interesting thought. All right. What if these numbers were not identical, but they were really close? Like what if I had a 4 and a 4.1 and a 3.8? That would mean that we still have a pretty decent quadratic model. It's just not a perfect fit. And sometimes that's the best you can do. is getting something that's close enough to being a good fit, because not everything in the world is going to be perfectly linear or perfectly quadratic. And so if these numbers are extraordinarily similar, you still have a good quadratic model looking at you. All right, one of the places that I prefer to go is actually to my calculator, because this tells me how good my fit's going to be, but it also tells me, switching screens, there we go, it also tells me the actual equation, so that if it is a good fit, I'm one step ahead of the program. So these are the exact same numbers I just had on my table, 1, 3, 5, 7, 9, negative 1, 1, 7, 17, and 31. And I'm going to take these and I'm going to run a regression. We've run linear regressions before. We go to the same spot, so this is on the menu, and we are looking for statistics because we would like the calculator to do some stat calculations for us. We can see linear regressions, which we have talked about. Hey, this is quadratic this time, so let's go to quadratic regression because that would actually make sense. Okay, so where are my x's? They are where I told you my x's are, because I labeled column A x, and I labeled column B y, and so I've just told it where the x's and the y's are. Okay, that's great. And now look at all this fun stuff that I have here. So we are talking, oh, that went really fast, never mind. Okay, let me do this instead then. There we go. We've got A, B, and C. Why do we have A, B, and C? Well, look what happens when I highlight this right here. I am seeing the full equation. If I click on it, it gives me the whole thing at the bottom here. AX squared plus BX plus C. Ladies and gentlemen, they're saying, hey, we ran a regression for you, and it's in standard form. AX squared plus BX plus C. And then specifically, these are your coefficients. So this thing is going to be 0.5 times x squared minus 1x minus 0.5. And so I have the equation. Now, how does this tell me if the equation is any good? I'm going to scroll down, and check that out. My r squared value tells me what kind of fit I have. And again, the closer to 1 this is, the better the fit. Quite frankly, this is 1, which matches what we said earlier. Because we got a perfect set of 4s constant when we did our differences, this is going to be a perfect fit. And that is the equation. All right, so basically with curve fitting, we are just kind of playing with things. We can run multiple models in the calculator and check out their fits using their r squared value. We might play with finite differences and see if we can learn something from that. Sometimes we just look at the graph and say, hey, these dots look like they could be in a line, or these dots look like part of a parabola. And we use that to get us started and going in the right direction as well. Okay, that is it. So thanks, guys.